As I told, this explicit as well as implicit representations are related with respect to your curves as well as surfaces. So, we'll start up with the explicit representation of curves. As we all know, basically curves, if you are studying with respect to two dimension, if you want to represent two dimension curve, how you are going to represent, that is y is equals to f of x. That is, you are defining a function with respect to x, which is actually assigned to y, that is y axis. Take an example of a curve in 2D plane, basically two-dimensional plane. This is two-dimensional plane, x and y plane. I have drawn a curve in this format. Suppose if you want to define curve in 3 dimension, the similar curve in 3 dimension. So this is the way this curve will look in 3 dimension plane, that is x, y, z plane. So this is how you will represent the curve in 3 dimension. Then there is one disadvantage regarding the explicit representation. You cannot represent all curves such as vertical lines as well as circles in the form of explicit representation. How? If you want to represent the similar two-dimensional curve in 3 dimension, what are the functions given with respect to it? The first function will be similar, that is with respect to y is equals to f of x, and with respect to z plane, this is the function given, that is g of x, that is with respect to explicit representation. Then how you'll be defining this z plane, that is the form z will be equated for the function with respect to both the planes, that is x as well as y. In 3 dimension, or basically in 2 dimension, how you define y is equals to f of x, but in 3 dimension, z is equals to f of x comma y, where you are including both the planes, that is x and y, in the function, which basically defines a surface with respect to that 3D plane. So this is how you perform explicit representation of curves. Then we have implicit representation. Similar to that of explicit representation, we have implicit representation. What do you mean by implicit representation? Implicit representation in the sense towards the plane, that is inner part of the plane. So how do you perform implicit representation with respect to two-dimensional curves? You'll define with respect to two planes x and y, that is g of x and y, which will be initiated to 0. The initial value of g of x and y will be 0. Then the advantage of implicit representation over explicit representation is it is more robust when you compare to explicit representation, because you can represent all lines in this, and you can represent circle as well, that is you can draw lines as well as circle. What was the disadvantage of explicit representation? You were not able to draw lines or circles. So with the help of implicit representation, we can even draw lines and plot circles by equating some equations, such as for lines ax plus by plus c, it is the general line equation which is equated to 0, and the general circle equation as x square plus y square minus the radius, that is r square, is equated to 0. So this is how you'll represent implicit representation for lines as well as circles. Then we have 3 dimension. This was about 2 dimension. How to represent implicit representation implementation with respect to 3 dimension is similarly with respect to 2 dimension x and y, you are just including the z axis, which is initially defined to 0, which basically defines a surface. That is, you're just defining a surface with the help of this functionality, with the help of this function. Then intersection of two surfaces, you will get a curve. That is, with the help of 3 dimension, if you want to implement implicit representation, you have to intersect two surfaces, with the help of which the resultant will be the curve. Then in general, we cannot solve for points that satisfy that particular condition. The simple disadvantage of implicit representation is it doesn't work with respect to points. So this was about explicit as well as implicit representation of curves. Then we have something called as algebraic surface with respect to the curves. Before moving on to algebraic surfaces, we actually have something called as quadratic surface as well as non-quadratic surface. What do you mean by quadratic surface? Basically, quadratic surface are basically used to define the class of the object. Class of the object in the sense, if you have some polygons such as triangle, square, quadrilateral. Suppose I take these three examples. What is the class of this particular polygons? Sorry, what is the class of this all objects? I can tell the class is polygon. All the three lies under polygon, comes under polygon. So why do we use quadratic surfaces? Basically, we use a quadratic surface so that it can define the class of that particular object. If I give triangle or a square, the quadratic surface should specify it is a polygon. If I give any other polygon, suppose a curve, if I define a curve, it should define it falls under curve. If I am defining a circle or anything, it should define it as a curve. So this is why we use quadratic surfaces. There are some reasons why we use quadratic surfaces. It is easy to compute, and then testing is also easy. But with respect to calculations, also quadratic surfaces works well. Then, basically, for example, quadratic surfaces, we have sphere as well as um, ellipse pod, that is actually some diagrammatic representation with respect to your quadratic surfaces. You need to just remember the basics of quadratic surfaces for moving on to algebraic surface. So, what is algebraic surface? This is the basic representation of algebraic surface, where we have all the planes x, y as well as z with respect to I, j and k. That is the initial value given to this particular planes. That is summation. Check out the summation. The starting point of the summation will be I, j and k, with starting with the value 0. If you are adding all the initial values I, j and k, if it is greater than or equal to 2, you will get a quadratic surface. Do remember this condition when you will get a quadratic surface. If the initial condition with respect to I, j and k values, if it is added, if it is summed, and if you get the value greater than or equal to 2, it is a quadratic surface. Then, how many terms does an algebraic surface or a quadratic surface consist of? It basically consists of 10 terms, which can also solve intersection with their ray by reducing the problem so that you can solve some quadratic equations. Then we have parametric curves. This is one of the type of curves with respect to quadratic surfaces as well. How the parametric curves are defined? Basically, parametric curves are defined by separate equations for each variable. That is, for x variable, you are giving x of u, y variable, y of u. This u basically represents the curve minimum as well as maximum values. Then z represents the z of u. Then, before moving on to these planes, that is x, y, z planes, we have to define a point with respect to which the curve is drawn. How the point is being defined is p of u is given by all the terms. That is, basically, you are defining all the terms inside the braces and taking the transpose of that particular term. That is, transpose of all x, y, z with respect to the curve. So this is how parametric curves are defined. You have a condition as well for parametric curves for u of max, the maximum value, and the minimum value. If it lies between u, that is the initial point with respect to the curve, we trace out a curve in 2 or 3 dimensions. That is, if this condition is met, you will say that the curve is in 2 dimension or 3 dimensions. So this is how this is an example of parametric curve. This is how a parametric curve look. XY plane, then points. PP are the points. This is the minimum value of the point, maximum value of the point, and this is the centroid value of the point where the curve is being located on 3 different planes, that is x, y as well as z. So this is how a parametric curve is being represented with the help of curves and surfaces. Then we have some functions related to curves, right? So how do you select such kind of functions so that the smooth functioning of the program works with respect to OpenGL? Usually, we can select good functions. how you will select good functions is not unique for a given spatial curve. That is, it should not be unique. That particular function should not be unique with respect to the curve. Then you will take approximation or interpolation of the data which is already known to you. That is, approximation of the data is taken. You can take approximation only for the data which you have already know, right? Because you cannot take the approximation for the data which you don't know. So that is one of the point to make a function work well. Then point functions which are easy to evaluate. If the functions are easy for evaluation, you can actually say you are taking a good step there. Then point functions which are easy to differentiate. If it is computation of normals or connecting segments, that is, if the functions are easy to check, if it which function lies in what terminology. If you are ready to identify that, you can easily say if you can perform computations or if you can provide segments to that particular functions. Then if all these conditions satisfy, we can say that particular functions work very smoothly. Then we have parametric lines as well. When compared to parametric curves, we actually have parametric lines. So what are these parametric lines? Parametric lines are nothing but, as I had defined parametric curves, similar to that of parametric curves, we have parametric lines as well. Basically, how do we define parametric lines is, it is based on the line as well as the point which is being defined to draw that particular line. Then we can normalize u to be over the interval. We basically provide interval for the parametric lines, that is u. With respect to u, I am defining the interval. The u should lie between 0 as well as 1. Line connecting 2 points P0 and P1. Take an example. P0 and P1 are the 2 points with the help of which a line is being connected. So how you will be defining parametric line is P of u. As I told, it should be between the interval 0 and 1. You are just taking 1 minus u of P0. That is, I am taking this as P of 0 as P0, P of 1 as P1, and just adding up P0 as well as P1 with respect to the points of that particular line. So this is how you define parametric lines. Then similarly, ray from P0 in the direction D. That is, as you know, I can calculate the point distance as well here from one point to another point. If you want to calculate distance, what I'll be using? I'll be using D here. To represent distance, I'll be using D. Similarly, ray from P0 in the direction D. That is, from P0, the direction moving for the next point is the distance D, right? So how do you give the parametric lines with respect to distance? You are just taking the product of the parametric data u, that is u into d with respect to the initial point P0, so that you will get the point P1. So this is how you define and calculate parametric lines. Then similarly, we have parametric surfaces as well. We studied parametric curves. Similarly, we have parametric lines as well as parametric surfaces. How parametric surfaces are defined? Parametric surfaces are defined based on two parameters, that is u as well as v. In basically, in parametric curves, we define just one parameter, that is u. In parametric surfaces, we have u as well as v. What does this u and v represent is, that is with respect to that plane x and y, what are the terms, that is parameters you are giving with respect to each and every plane. As you can see, the surface of the parametric curve is being represented in three planes, that is x, y as well as z. The v value is given here 1, here is v, and here is 0. As you all know, the interval with respect to parametric terminology should lie between 0 and 1. You can check out the v value lies between 0 as well as 1 in the plane. So similarly, I will define all the three planes. How you will calculate the parametric surface? You are just taking the transpose of all these functions. Then some of the properties related to the curves. It has very good smoothness. Differentiation of that particular curves is very good. Then it is easy to evaluate. Then these are some of the properties related to curves. Then similarly, we have parametric normals as well. These are some of the topics that covers the curves as well as surfaces, that comes under curves as well as surfaces. We have normals as well. So what is a normal is basically you can check out in the diagram represented. If this is the surface you are defining, and if you are placing a plane onto that particular surface, you should define one point with the help of which you can differentiate that particular plane. So at that position, whatever the point you are defining, that is P, that is actually called as normal here. That is, we can differentiate with respect to U and V to obtain normal at any point P. The direction from the point P from which the plane is specifying the other angle, I can tell that particular direction as N. How that particular parametric normal is defined with respect to this particular matrix it is been defining. So whatever the parametric normal is, you are just taking the product of these two. Then we have parametric planes as well, with respect to vector form as well as point form. The first block says it is an vector form of parametric plane. The second block says it is an point form of a parametric plane. So how do you define a vector form of a parametric plane is, basically, first you will take the product of the number of planes here. There are planes defined here, that is the sides defined of that particular plane as R and Q. You will take product with respect to U and V, that is the parameters of the plane initiated with P naught, and then finally you will take the summation of that, so that you will get the point vector of that particular plane. How do you calculate N? N is just you are taking the product of the sides, that is R and Q, or Q and R. So this is how vector form is represented of a plane. Then similarly, we have point form of a plane, which is just making subtractions. Points, as you can see, there are 3 points here. With respect to points, I can define Q as P1 minus P naught, where R is defined as P2 minus P naught. That is the next point, that is the final destination point with respect to initial point, destination point with respect to the initial point. So this is how you calculate the 3-point form as well with respect to the parametric planes. Then we have sphere as well. Similar, what does sphere tells? It is actually combination of ovals, right? Sphere. So how do you calculate the parametric sphere is with respect to two parameters U and V with respect to some angle, that is theta as well as phi, that is r cos theta sine phi. Then with respect to y, r sine theta sine phi. With respect to z, you are just taking the cos terminology. Then check out the condition where the theta as well as phi should be lying onto the sphere. If the theta is greater than or equal to 360 degree, then only you will get an x as well as y coordinates which are using theta. If you want to use phi in your function, it should be greater than or equal to 180 degree. At this time only you can tell a parametric sphere has been generated. Then what is basically theta as well as phi represent? As you all know, it is a constant which basically tells you the circles of longitude as well as latitude. How do you show the differentiation between the normal as well as the parametric sphere is? You'll just give an equate a symbol, that is n is equals to p. That is differentiate to show n is equals to p. So this is how the parametric sphere has been represented. Then now comes the actual topics, that is curve segments. So what are these curve segments? Now we studied parametric curves as well, how the parametric curves are represented and all. So keeping that as an initial knowledge about curves, will start up what are curve segments. So in curve segments, basically we'll be normalizing some terms, that is u, that is you are initializing some values to u and then you'll represent the curve. Once you normalize u, how the curve equation can be written as, that is p of u with respect to point, you are just taking the transpose of all the terms, that is x, y as well as z, where u should lie between 0 as well as 1. That is the initial term we studied in curve surfaces as well. That is curve terminologies. Then in numerical methods, we basically design a single global curve. That is how to start with curves. You basically start drawing with single initial curve. So that is a method where you can tell it is a classical numerical method where you are just drawing a single curve. There. In how we'll use this curve segments in our computer graphics. In computer graphics, it is better to design small connected curve segments such as this. This is one segment and this is the another segment. So we'll be using these kind of curves in computer graphics. How this curve is defined with respect to different points, right? There are three different points. With the help of these 3 points, they are defining the curve here. So how to join all the curve? You are just joining the point with respect to the curve segment, that is q of 0, which is actually initiated here. So that is how the curve segments are defined. Then we have actually in detail about the parametric polynomial curves. In parametric polynomial curves, we'll be using the parameters x, y as well as z as the plane. How these are being defined is we'll just check out if the condition n, m as well as k, that is the termination condition of all the planes n, m as well as k. This might be k or l as well. If it is all are equal, we need to determine coefficients. That is, you will just increment. You will take the first increment of the first termination condition. That is 3 times of that particular coefficient. Then equivalently, we need this condition to be independent on some other conditions as well. That is, it should be liable to all these conditions. That is y as well as z. Then nothing that the curves for x, y as well as z are independent. We can define each term independently in an identical manner. That is, if this condition satisfies, all the destination terminology should be equated to the single value. Then how finally you can represent the polynomial curves with respect to c as well as u. Basically, you can check this might be k or l as well, which is actually an termination condition with respect to the polynomial curves. So why we'll be using polynomial curves? It is actually easy to evaluate. These are some of the advantages of polynomials. Why we'll be using polynomials? Easy to evaluate, continuous and differentiable everywhere. That is, you can use polynomials anywhere so that you can differentiate what kind of polynomial we'll be using in any functions. Then must worry about continuity at joint points, including the derivatives. That is, if you are using some points with respect to polynomials, you need not worry about how the continuity is being done, but you have to worry whenever there are the derivatives with respect to that points, the continuity should be tracked off. So this is how a polynomial curve is being represented with respect to 2 points where you have joining points as p1 here. So we have cubic parametric polynomials. As I told, with respect to this module, each and everything will be related to your software part as well as hardware part. We studied some of the hardware devices as well. Now we are actually studying how to represent such kind of curves, surfaces, and all with respect to the software OpenGL. In cubic parametric polynomials, we have a condition, that is the termination condition n, m as well as l should be equated to 3. So this is the initial or the final destination point where all the termination conditions should be met here. That should be equated to 3, which basically gives balance between evaluation as well as flexibility in the design. If this condition is met, if n, m as well as l is equated to 3, there is actually a balance between evaluation with respect to the flexibility of the design wherever you are designing a polynomial. So how do you represent a cubic parametric polynomial? Is with respect to similar equation of a polynomial, you are just representing the condition where kth value should start from 0 to 3. In cubic parametric polynomials, we have 4 coefficients that is used to determine the plane, that is each plane is determined based on this four coefficients, that is x, y as well as z. You can find x, y as well as z with the help of these coefficients. Then these four independent conditions for various values of mu resulting in are unknown for each of the plane x, y as well as z, which basically links to this point. Then we have some conditions with respect to that four terminologies. What are those conditions? Conditions are a mixture of continuity requirements at the join points and the conditions for fitting the data. The conditions which will be applying onto the four equations which are used in the cubic parametric polynomials, they are basically used to join the points as well as the conditions for fitting such kind of data. Which kind of data? The data is of cubic parametric polynomial. Then we have surfaces as well related to polynomials, how the cubic polynomial surfaces are being drawn. Cubic polynomial surfaces are being drawn with the help of these functions, that is x of uv, y of uv, and z of uv. You are just taking the transpose of this particular functions. Where how do you define p of uv? It is just the summation of I is equals to 0 to 3 and z is equals to 0 to 3. With respect to the curved surfaces, you are defining both the terms u as well as v. So what is where does this p lie? Is p can be lying in any of the plane, that is x, y, or z. We need different huge number of coefficients so that you can define cubic polynomial surfaces which are actually dependent on some other set of coefficients, so that you can determine such kind of surfaces, that is cubic polynomial surfaces. Then how to represent cubic polynomial surfaces in the form of matrix vector? You'll calculate the value of c as well as u. Once you have got the coefficient values as well as the u value of that particular points, you will define c with respect to a matrix and u with respect to the matrix. Then you are just taking the transpose of this and giving a product with respect to c, that are the coefficients, or it might be vice versa as well, so that you can represent the matrix format of that particular surfaces. Then we have another type, that is interpolating curve. This is the second type of your curve. What is this interpolating curve is? You can check out in the diagram. There is a simple curve drawn with the help of points, that is P0 to P3. How this interpolating points is defined is, interpolating curve defined is, first given four data that are actually called as control points P0, P1, P2, and P3, which basically determines cubic P of u which passes through them. That is, you can see the representation of the curve is in the form of a normal curved surface. So at this point, you can tell there is some interpolation happening with respect to the point, so that you can define the surface, you can define the curve onto the surface. So before finding out the interpolation of the curve, you need to know the coefficients of that particular curve, with that can be found with the help of C0, C1, C2 as well as C3. So this is how you will find the interpolating curve with the help of coefficients. Then there are some equations to calculate P0 as well as P1. It is just the product of the coefficients with respect to u. How the interpolating conditions with respect to u is defined as, u starts with 0 and ends with 1. As we all know, the termination condition, initial condition should be 0 and the destination condition will be 1. The points lying between 0 and 1 is 1/3 of the point and 2/3 of the point. Check out how the P0, P1, and P2 and P3 are calculated. P1 is calculated with respect to C0 plus 1/3 of C1 plus 1/3 the whole square of C2 and 1/3 whole cube of C3. Similarly, with respect to point 2 as well. First, you will be calculating the points, and then with the help of these points, a curve is being drawn onto the surface. Then how to represent this this in the form of matrices? You are just taking the transpose of all the points here, P0, P1, P2, and P3, and putting it in the form of matrix here. Okay, so this is how interpolation equations are calculated. Then the final interpolation matrix, if you are finding it by giving some value state, so this is how it will look. You can see there are almost negative signs here because the data which you are passing, it should be dependent onto the interpolation data. It should actually match with respect to that. You can check out how do you calculate mi. Basically mi will be taken from the coefficient with respect to the points here. Basically, MI does not depend on the input data and can be used for each segment. This is actually not dependent on any of the data. It is in the form of independent data, which can actually be taken for any kind of curves and surfaces. Then we saw how to interpolate segments with respect to single data or single points. Now we have interpolation with respect to multiple segments. So how interpolation occurs if you are using multiple segments? You can see the curve drawn here. It consists of huge number of points starting from P0 and ending from P6. So what is the case if you have such kind of points? How the curve can be defined? You can tell such kind of performance as interpolating multiple segments. That is, you will draw one curve with the help of P0 to P3 and the other curve with the help of P3 to P6. That is, the first point, that is with respect to interpolation P, I can define it as a transpose of P0 to P3, and the second I can define it as transpose of P3 to P6. That is, you need not give continuity to the curves with respect to interpolating multiple segments. You can get continuity at join points, but not continuity of derivatives. That is, you can tell these are the join points, right? So with the help of these join points, you can define two different interpolating segments with respect to multiple points. So this is how interpolating multiple